Now it is my pleasure to introduce Vikash Mansinghka. He is a research scientist at MIT, where he leads the Probabilistic Computing Project, which does a mix of basic and translational research aimed at engineering intelligent systems that can be our partners rather than our replacements. Previously, he co-founded two VC-backed companies that commercialized components of the open source probabilistic computing stack, one of which was acquired by Salesforce in 2012. He has degrees in math and computer science from MIT, as well as Masters of Engineering in Computer Science and a PhD in computation, and he has advised startups, enterprises, and philanthropic organizations, including DeepMind. He is a co-founder of Empirical Systems, a new venture-backed AI startup aimed at improving the credibility and transparency of statistical inference. He's here today to speak about his project BayesDB and how it can help us analyze data for humanitarian causes. Please join me in welcoming Vikash Mansinghka.
Thank you. Can you guys hear me okay? Okay, great. So what I thought I'd do today is spend a few minutes trying to talk a little bit about the difference between AI hype and reality. And then against that backdrop, talk about some new technology that I think does create new opportunities for doing good by analyzing data that's largely already public in support of causes that are in the public interest. And maybe the last 5 or 10 minutes of the talk will include a couple of examples of BayesDB, but for the most part, this isn't going to be like a hands-on talk. It's sort of more about the fundamental issues and opportunities. Okay. So for decades, the field of AI has tried to account for its progress by measuring its ability to beat top-performing humans at their own game. So I remember Deep Blue defeating Kasparov and Watson defeating Ken Jennings. More recently, AlphaGo has had a number of successes. And I think these do represent important milestones in the progress of machine intelligence. But when I talk to my colleagues in AI, I find myself mostly pointing out how they highlight the limitations of AI. So consider that many children know the rules of chess, Go, and Jeopardy. But Watson can't play chess or Go. And AlphaGo can't parse English. Right, so the human mind can sort of flexibly learn about all of these domains, but getting any one of these AI systems to solve very simple versions of the task solved by another would be an enormous research project that would probably fail today. So although there's a lot of exuberance about AI, this is a piece of marketing material from IBM about Watson, and about big data applications and how that's going to fundamentally change our approach to knowledge. It turns out that some of the same advertisements have been run by IBM since the 1960s for some of the first computers. Right? The basic narrative that we have this giant brain that's electronic that we can treat as an oracle to solve problems that are beyond us, either individually or collectively, is not a new one. And I think it is misleading. So here's one way to understand the difference. Let's contrast Watson with Dave Ferrucci, the chief scientist who led the team at IBM Research that built Watson. Admittedly, Watson could beat Dave at Jeopardy. However, Dave could negotiate the interpersonal relationships that were required to construct and lead a team to build Watson. And Watson uses computing elements that were clocked at 3 gigahertz and collectively consumes 80 kilowatts of power, whereas if you think about the neurons in Dave's brain as switching elements, they're maybe optimistically clocked at 100 hertz. and he can run all day on a cheeseburger. So it's also the case that when you look at data analysis, the types of questions that we could ask, at least in the 80s, and the questions we could ask today, are essentially the same category of questions. All right, so I would argue that there were fundamental shifts from the pre-relational database era to the database era, where you could articulate questions like, show me payments from some transactions database aggregated by month. But conceptually, the operations that we're automating have been the same for decades. It's true that the cost of storage has decreased by many, many orders of magnitude over this time period. And the cost of computation has as well. So in this graph, the only thing I want to point out, so here we're measuring the cost of computing power equal to an iPad 2. So an ENIAC, 1950, would have cost, let's see here, thousands, millions, billions, about $1 trillion, or a few $1 trillion, to use that technology generation to do as much compute as an iPad 2 has. So these are fundamental shifts. But we don't have intelligent algorithms that somehow learn like the brain. What we actually have is modern system software, vastly more data and compute, and therefore the ability to do calculations, especially statistical calculations, in ways that just work better now. So when you try to take the ability to calculate and use that to construct intelligence, one way to look at it is that there may be three very fundamental schools of thought on this. There's statistical inference, there's logical deduction, and there's heuristic search. And all the AI systems I mentioned at the beginning of this talk use all of these approaches as components. Lately, statistical inference has gotten a lot of play, but heuristic search was just as important for, let's say, AlphaGo's success. It was really an integration of these two. But intelligence is not just about pattern recognition or logic or search. Our psyches can explain things, they can imagine things that we could potentially see in the future but haven't seen yet. They can help us orchestrate planning processes that help us manifest possibilities that have previously only been in our psyches. And they let us build new models as we sort of move through our experience. And mature intelligence also includes the ability to understand the strengths and limitations of our models and our intelligence. None of these capabilities are really manifest in even the best state-of-the-art AI systems today. So my lab's been trying to build AI systems that can collaborate with people and serve as assistants rather than replace them. The mode of interaction is that you have a human supervisor that might offer guidelines or questions or hints to an AI assistant. And the AI assistant will respond with, in some cases, partial solutions and some recognition that there's uncertainty. So from a technological perspective, this requires an ability to develop languages for encoding guidelines, questions, and hints, and partial solutions and uncertainty, and exchanging them between people and software. And probabilistic programming, which is an emerging field at the intersection of programming languages and probability theory, sort of been growing for the last 10 years or so, has provided a lot of those building blocks. So over the last few years, I've learned that I think there really is a pressing need for this kind of AI software. So in some work with the Gates Foundation, for example, I learned about how hard it is to do, a little bit about how hard it is to do empirically grounded policy advocacy. So here's a problem that the foundation faces on a regular basis. They fund primary data collection internationally. They have access to a network of domain experts. And they want to solve problems, like they run a study in Bangladesh, and they want to know, should they try to convince some government in Kenya to adopt the recommendations of that study? Are those recommendations generalizable, given how essentially uncontrollable all the variables are? And what if the cost is high? How do they make the case? This is partly hard because statistical inference is not a reliable technology. So recently, a group of researchers did a controlled trial asking the question, does statistical data analysis replicate? So they took the question of, do soccer referees give more red cards to dark skin tone players or light skin tone players? And they did a controlled experiment where they gave 29 teams a single data set and the same question and said, go answer it. And the answers they got, it's like 20 teams found a statistically significant positive effect, and 9 teams observed a non-significant relationship. And so the same data set, the same question, qualified analysts, and answers that don't agree. And when we think about replication crises in social psychology or in medicine, I actually think they're partly merely symptomatic of a deeper replication crisis in statistical inference. That's largely unacknowledged. One could argue that this replication crisis is driven by the need for good judgment to do credible inference from data. And judgment is necessary first to wrangle with data challenges. So how do you deal with missing values or data of many different types? Actually, let me just ask the audience a question. How many of you guys have tried to analyze a CSV file or a spreadsheet doing some kind of statistics? Great. And how many of you believed that you got the essential truth of the matter by doing that process? Some of you, good. Excellent. So I'll try to talk a little bit about the circumstances where I think that's possible and situations where I think there are technological limitations. So that's encouraging. There are also inferential challenges. So in many cases, we're trying to study heterogeneous phenomena. So that means even if you have vast data sets, there are few real replicates. You might have 10,000 uncontrolled covariates quite easily in these public health questions. You know, if you're studying geographical regions, small geographical regions like villages. You would typically have convenience samples, not randomized experiments. If you have randomized experiments, there are issues of imperfect randomization and control, which are largely unaddressed methodologically. I mean, they're left up to the judgment of the statisticians, who hopefully are able to wrangle with them. And often our causal knowledge is so limited, we don't know how to prune covariates a priori. Also, the distributional assumptions that we tend to make, I think, are really unjustified. So when I teach MIT students statistics, I show them this data set. Each row is showing the latency histogram, so the histogram on response times of a computer cluster to a set of queries. And if you zoom in, we'll see these black bars denote the empirical mean of each histogram. So even in the case where the distribution is unimodal, none of them are well summarized by the average. And so every time I write a paper where me or one of my students says, assume the distribution is Gaussian, I sort of feel like I need to look at a framed picture of this for at least a minute, just, you know. MIT students tend to think that executives don't trust quantitative reasoning because maybe they're just not comfortable enough with math. I find myself teaching a very different viewpoint. That the reason decision makers often don't trust statistics is because unless, as Churchill points out, that he doctored the statistics himself, there's no confidence that qualitative truth will be respected by the analytical methodology, you know, if the situation isn't just a very simple scenario. And the distrust of data analysis is widespread. Andrew Gelman, who helped inspire the BayesDB project, which I'll start talking about in a couple minutes, puts it this way. So he, you know, actually, how many of you read Andrew Gelman's blog? Okay, so I highly recommend it, especially anyone who does data analysis and doesn't read his blog at least occasionally. So it has maybe a few tens of thousands of readers, which is maybe the only statistics, like the only piece of writing on statistics anywhere that has that readership. And Andrew says, statistics is hard, like basketball. We have to accept statistical incompetence not as an aberration, but as the norm. And I think this is true. So we're not going to solve these credibility issues merely by increasing the rate at which we train statisticians. If we're interested in humanitarian problems, we also won't be able to afford to hire statisticians if we do train them. I was recently talking to my dean of undergrad education about how MIT is maybe missing an educational opportunity because we don't know how to train good statisticians or data scientists from undergrad. And just recently, data scientists overtook various forms of software engineering as one of the highest compensated and most sought after professions. So for public interest problems, humanitarian problems, there's this real shortage of good judgment. That experience is what led us to work on BayesDB. So BayesDB tries to provide AI assistance for data science in that collaborative mode I was describing earlier, where you have a human supervisor who's expressing guidelines and hints and asking questions, and BayesDB is giving back solutions. In some cases, they're quite partial with some measure of uncertainty. And our focus so far has really been on the first stages of data science and the Hopkins taxonomy of data science, so descriptive and exploratory data analysis. And that's actually where most of the commercial work so far has been. I wouldn't say that BayesDB is mature technology for these problems, but I will say that it has been battle tested. And there are open source components of the BayesDB backend that were built by engineers at Google and Salesforce, and sort of are fairly trustworthy pieces of distributed systems infrastructure. A lot of our research in the lab is sort of moving towards more causal and mechanistic analysis. And really our goal, which I think we've taken some meaningful steps towards, is to build an AI that can let someone with domain expertise do in seconds or minutes what currently takes hours or days for someone who has good statistical judgment. So what do I mean by data science? So how many of you have seen Drew Conway's data science taxonomy? OK, this is great. So one view is that data science is really at the intersection of programming, statistics, and domain knowledge. So if you have all three of those skill sets, you can then come to credible inferences. If what you have is programming and statistics understanding, you can do machine learning. If you have statistics and domain knowledge, but no programming skill, you can do traditional quantitative research. And if all you have is domain knowledge and a lot of data, then you're at the risk of rapidly producing misleading results. OK. So BayesDB is a system whose architecture parallels the architecture of a traditional database, except instead of letting you ask and answer questions that are about the contents of data, it lets you ask and answer questions that are about its probable implications. So here's a transcript, just on a toy example. So I might create a data table from a CSV file, then create a population which represents the abstract, idealized conceptual population of interest, and ask BayesDB, guess the data types. Then build an ensemble of models under various assumptions, mostly just using some baseline technique. And then generate simulations. So generate a synthetic data set showing the age and state of virtual customers, assuming their income is $145,000. So lots of technical challenges we had to overcome to make this possible. Everything is open source, and the mathematical basis is all freely available online. I won't go into the details here. I will just say that for people who have done a lot of statistics, I would say the real surprise was number one, developing techniques that could emulate the judgment calls that a good data analyst makes in analyzing a multivariate, messy database. The other two were challenging, but one is the one that's maybe the most technically surprising that it was possible, and that took about 10 years. So the vision for BayesDB in an organization like the Gates Foundation is as a medium, an intelligent medium, to enable collaboration between policy advocates, domain experts, field researchers, and statisticians. So let me just sort of wrap up by giving a couple of very quick examples and ask you guys for some help. So most of this work is funded by DARPA. So I'm going to use an example from a database of Earth satellites. So you got a bunch of variables about satellites, the kinematic properties of a satellite's orbit, the country of the operator or the contractor. And this is a visual representation of the database where each row is a satellite, and a red cell, each column's a variable, and red indicates missingness. It's a messy database. You can analyze this in BayesDB and then answer questions like, who is probably operating some satellite if all I know is that it's in geosynchronous orbit and it has a dry mass of 500 kilograms? So I do that by saying simulate the country and the purpose, given the orbit class is geosynchronous and the dry mass is 500 kilograms. And I can see the results stream in, and I get this broad distribution on outputs that captures complex dependencies. And in this case, is basically saying, I don't know. Right? The most likely outcome is US communications, but that's less than 25% likely. You can also use BayesDB to do things like AI-assisted data cleaning. So find me the satellites that are purporting to be in geosynchronous orbit, but where if you make a judgment call about how probable their orbital period is, you're going to sort from the least probable on up, you find satellites that couldn't possibly be in geosynchronous orbit around Earth, because 140 minutes is actually a decimal point placement error, most likely, as the same with 14.36. I'll just point out that 140 minutes is not an outlier. There are many satellites that have periods of around 2 hours. It's just an anomaly if you consider all the other variables that predict probability of orbital period. OK, so if you go to public interest problems, I think there's some exciting new opportunities here. So unlike data analysis problems for business operations in the enterprise world, in the public interest world, you can't design your operations to minimize these problems. Right? It's like Starbucks can construct rules of management that help to mitigate these challenges, and they can force uniform IT adoption and all this other stuff. Schools can't, courts can't, hospitals can't, police departments can't. Right? They have to sort of somehow confront these problems even when they're just doing very basic reporting. So making a report card for the Chicago Unified School District is an intense statistical inference problem. We started to look at data in this vein, so I'll just give one example. We took a look at the Dartmouth Atlas of Healthcare years ago. So it's got a bunch of variables about the cost and capacity of hospitals. And this is a map where you ask BayesDB, show me a map of the probability that all these variables predict one another. And all I'll point out here is there are these 4 quality score variables, which are survey instruments talking about the quality of care of a hospital. And this map is saying that these variables are probably independent of all the variables about the operating structure and cost structure of the hospital. So when we first saw this, we thought this must be a bug, because we don't know anything about healthcare. It actually turns out that this finding was a key finding in the design of the Affordable Care Act. And it was written about in the New Yorker. I mean, obviously, from work done by the Dartmouth Atlas of Healthcare. This just happened to be a replication of that negative result. And if you rank hospitals by comparing their real value of the number of doctor's visits per person who died, shown in red here, with a predicted histogram of what BayesDB thinks the value should be on the basis of all the variables, you find that hospitals like McAllen, Texas have this huge skew where you'd expect them to have lots of doctor's visits, but they have far fewer. Right? It turns out McAllen was the anecdote used in the New Yorker article to describe this strange dissociation. OK, so let me wrap up. So I'm a US citizen. And it turns out that in the US, it's illegal for the Bureau of Alcohol, Tobacco, and Firearms to maintain a database of guns based on their IDs. So when a police department does a gun search, that's serviced by a bunch of people looking through microfilm. And we can recognize that this is absurd, arguably criminal, I mean, in a moral sense. We know it's absurd because of AI. And we don't think of the database as AI technology, but it is. Right? We would have expected that this AI system would have obsoleted this whole human process decades ago. I think we're going to start entering a world where existing empirical inference processes start to seem obsolete in the same way that this does. And I think that creates enormous opportunities to do good based on public interest data. By letting people ask questions and leaving it up to the machine to at least give baseline answers. And over time, I think we can get to more and more interesting types of questions that can help inform policy. Although for now, I think the opportunity is maybe quite substantial, merely in understanding what does the data that's already out there tell us about what's probably true. So I have 4 requests for help from you guys. This is my last slide. So the first one is, we're at the early stages in my lab, in partnership with people at the Media Lab, of trying to build multivariate maps of poverty, inequality, and psychological suffering using this technology, and building an open source mapping layer, some distributed cloud infrastructure to host it, and ideally a Google Spreadsheets interface and tools to help enable people to advocate for their own interests on the basis of this data. So that's something that there may be EAs who are interested in helping with, or connections that could be made. Second, we're very interested in methodological research about the generalizability of studies given imperfect randomization and control. Third, I should say we're, as a culture, in my lab, pretty skeptical of quantitative metrics that are deterministic. I was talking yesterday with people here about the difference between GDP and dollies, let's say. Right? I didn't know what a dolly was until I had that conversation. So clearly the EA community is very interested in metrics. But AI made so much progress in the last 20 years largely by recognizing that we don't actually know what's true deterministically. Right? We only know what's probably true. And people like Stuart Russell are now arguing that a similar revolution needs to take place for the treatment of what we want, or what we value. That the integration of probability into our notions of metrics or goals or values will have fundamental change. And there are ways that BayesDB can help with this, to help us empirically make more robust measurements of what we want and whether what we want is being achieved. And I'd love to collaborate with that. Although some of that is a little philosophical, I think it's actually very practical as well. And then finally, there's some interesting work integrating BayesDB with blockchain that may be appealing to some of the tech people here. So if you're interested in helping, I hope you will contact me. Thank you.
Let's have a seat. We've got some questions.
Great.
So exciting technology. I'm really enthused about this. This is a challenge that I face on a daily basis. We were talking a little bit before.
Yeah.
I have, in some ways, an idealized case that I confront every day because, just for everybody's benefit, I'm leading a software company, and we've got pretty good user data. We can log stuff.
Yeah.
And we have Google Analytics. We have our own database. We have a lot of things, and it's still really tough a lot of times to know if you're getting anything right or wrong. So I guess the first question that I would ask is, you said this is sort of open source and available. Like, what is the status of, say, my ability to download and use this, and what can I do to get my hands on it?
Yeah, that's great. So so at one level, there's GitHub repositories, and you can find stuff from my lab's website, and so at that level, it's all available. However, having done a couple of tech startups, there is a big gap between research prototype and product that meets some availability standards. So I would say that my lab is just now transitioning BayesDB from being the open source research prototype version, as opposed to the parts that have been commercialized before. OK, yeah, let me explain it this way. So if what you're interested in is just baseline analysis, there's an open source thing that was, came from one of the startups I was involved in, improved by people at Google and Salesforce. It's got protocol buffers on the interface and is like a messy, C++ Python distributed appliance. That is a total pain to use, but if you wanted to stream data through, works, and has been battle tested quite rigorously. If you want to do interactive queries and exploratory data analysis, you could use our research prototype. We're using it actively with collaborators, but we're still right now maintaining relationships with each collaborator. So the software is available, but the support is not. I would say that for use cases which are like small startups, or medium-sized startups, or companies that aren't, doing some strategic AI initiative that this is a part of, I would say that, I would wait at least 3 to 6 months, unless you have an engineer who's so excited about this technology stack that she wants to learn about it, and then plenty of people have used it successfully that I never know, and then they send me emails, and I was like, oh my God, you tried that? Okay, so.
So the research prototype, is that kind of, you showed a few example sort of
all of these are
line
from
sequences.
that. Yeah,
so that's kind of
right.
what it would look like to
Well, we have a
with that.
Jupyter notebook and an interactive plotting GUI that's JavaScript based. There's like a little mini language for plotting that backs out into D3, and there's a bunch of bells and whistles.
Now, do you envision this becoming a production database in the sense that my company uses Postgres,
Yeah,
and
right.
it's obviously that's an old technology that's
Yeah.
got a lot of love over the years.
Yeah.
Do you envision trying to kind of rival that and be sort of the main home of data, or is this intended indefinitely to be sort of a side system that sort of pulls data from that and does stuff with it?
Yeah, fantastic question. So when I came back to MIT, the first person I went to visit was Mike Stonebreaker, because one of his students ended up co-founding my second startup, but also because Postgres was produced by a generation of master's theses at Berkeley. So it became production ready over a long period of time. I think there's a path for that for BayesDB. For BayesLite, which is the SQLite 3 embedded version of BayesDB, which our research prototype is based on. But I don't think it's ever going to be like the system of record, right? It's really more about helping people ask and answer questions once they've already gathered the data in some other way. However, I do think that this work invites the question: how would you design a distributed data storage infrastructure, whose purpose is not to log transactions, but to help people arrive at truth, by encoding their empirical, their experience. And that's something that's related to that blockchain project that I mentioned. That's at very early stages, but that will be evolving over the next couple of years. Yeah. Oh, and I should say that the open probabilistic computing stack, which will be a provisionable version of the open source research platform stuff, I will be encouraging some companies to play with it in 3 to 6 months.
Cool. So on the theme of kind of human and computer working together, in my own experience, and certainly on our team, I feel like one of the hardest things to teach has been the kind of distrust of data, really. It's so
good.
easy to.
I'm so glad you're trying, though. That's
well, and
I
I'm
think
trying to teach myself to continue to do it as well. How would you describe the process of kind of coming to trust? How is it different to work with this system? Do you sort of build a different kind of
Yes.
trust or a different kind of distrust? Because I'm always kind of like, I don't know. It's always tough, right? Like, there's always this nagging doubt.
Yeah.
Does that still exist? How does that feel, and how is it
fantastic question. So I'll just give a hint of an answer. So when I talk to a consultant about a domain that I don't know very much about, maybe when you do, let me ask you a question. How do you build trust in them?
I probably ask questions I at least have an intuition about the answer to,
Exactly.
and see if they can
That's right.
answer it correctly.
So BayesDB facilitates that dialectic in two ways. One, you can compare the results of SQL selecting subsets of your data with simulating from the baseline models for those same queries. And that is a generic way for corners of the problem space where you have enough data for SQL select to be meaningful and enough trust that you understand the sampling assumptions to just see, okay, how well is BayesDB capturing the patterns that you know to be true? That's a part of the answer. Another part of the answer is you can use simulate with BayesDB plus a domain expert who can judge whether the results make sense or not to say qualitatively, do I buy these conclusions or not for various patterns of questions. Right? So the interface for BayesDB, I think, makes it much easier than it has been in the past for a domain expert who just is qualitative to do ad hoc interrogation of what does the thing know about, what does it not know about, is it appropriately uncertain or not. That's not a complete answer by any means, but that's the mode of trust building that I find the most compelling. If you're a statistician or a data scientist, then there's a whole technical dialectic you can also engage in, which my papers are talking about in bits and pieces, and there are some fundamental research questions there too, right? Like for example, one of the things BayesDB is stepping towards is more of an agile process for empirical inference, where you actually have testable, intermediate, formalized results. So then it's like, what are unit tests for statistical inference? And like, what's the regression infrastructure, and how do you deal with data drift? And so there's that whole thing, and that's like more of a research program. What are verification tools for empirical inference? And that's something that I have grad students working on.
Even just to be able to flag possibly or probably wrong data.
That's right.
would be an unbelievable advantage, I feel like, relative to where most people sit today, where they sort of do the analysis. This is certainly what we do. We do the analysis, then we sort of get this gut feeling that there's a problem, and then we go looking for the wrong data that may have caused it. Sometimes we find it, sometimes we don't. Sometimes we can sort of begrudgingly say, well, I guess this must be what it is, even though it doesn't feel like it should be. So yeah, even just to be able to kind of say, hey, here are some things that look like they may be just muddying up your environment before you get started.
When I'm talking to big companies, I often ask them the question, what fraction of your data warehouse do you think would survive a given probability threshold of being correct?
Yeah.
Hey, could you pull out your phone and ask some of our questions?
Yeah, I've got, I'm trying to use some of them as I go. One that I was just getting to now is sort of I think you're trying to address a danger of people making, the wrong, trusting data too much, right?
Yes.
Is there another sort of data that emerges with this type of system?
Danger, you mean?
Another sort of danger, yes,
Yeah,
that emerges with this sort of system where because you sort of take one thing off the table, people can sort of shoot themselves in the foot in another way. Have you observed any of that kind of dynamic?
Well, I would say that when we first released BayesDB years and years ago, no, I shouldn't say released, when DARPA required us to put the first master's thesis on BayesDB on the web, and we got support emails from the College Board the next day, I was very worried about this. Because at that point in time, there wasn't an interface for statisticians to put in quantitative knowledge they had, or to really get all the diagnostics about the AI's baseline modeling. And there were some sort of rather harsh things on Twitter that were said about BayesDB by statisticians. I mean, one quote was like, "This is like giving children a loaded gun." And sort of, I had two responses. My first one was like, "So is OLS, buddy," But then my second response was like, "Yeah, okay, we need to be sort of circumspect about the real potentials and danger." So now with BayesDB, we make it possible for statisticians to do various kinds of model and inference quality and to put in quantitative modeling assumptions to override the AI baseline when they have it. But I'm very concerned about this question of how do we basically build a medium that lets our culture develop a healthier relationship around empirical inference and trust in data and distrust and skepticism. And that's a big question that has cultural components, educational components, user interface components, back-end components, and I'm very interested in enabling people doing work on all facets of that.
Couple questions from the audience. Can you talk a little bit more about the example surrounding PTSD and military use that I think you mentioned briefly, but...
Yeah, that's right. So there I'll talk mostly about what I think we might be able to do based on analyses of data we don't yet have the rights to talk about publicly. So we've been able to do preliminary analyses. So the VA has one of the most mature health records. And it turns out that for those who maybe don't know, the Army has been very interested in understanding stress resilience and the causes of PTSD and vulnerabilities for various kinds of presentations of trauma after combat and injuries. There's a survey called STARS, which is a multi-year project where every new soldier in a certain cohort was given this extensive background history around childhood trauma and like all kinds of other stuff. And so, and I think it's widely recognized that PTSD, psychological health, suicide are enormous, like crushing problems in the veteran community in particular. They're also problems that our culture is facing, and that veterans are treated very shabbily. You know, I mean, the average number of psychoactive drugs that veterans are given, you know, and the rate of psychotropic prescriptions from the VA, it's, you know, for people who don't know about it, it's really, at least I found learning about it a little bit really eye-opening. So one of my hopes is that we can start by taking a look at that population and those data and give that community tools for reporting adverse events more honestly, you know, accounting things as adverse events to drugs that are real adverse events, like kinds of hair loss or trembling that aren't considered adverse events in the formal pharma taxonomy because of reasons I honestly don't understand. And start to build a better empirical map of the relationship between, you know, risk factors for various kinds of suffering and the, you know, what members of that population experience. And it'll be a multivariate thing. And ultimately, I hope that this will help us ask better questions about the diagnostic criteria in the DSM, which some of you who are interested in mental health may know about. So that whole area is one that I'm in a brain and cognitive sciences department, so there's a lot of interest in that category of questions, both hopefully in a way that could help people in the near term and to address some very basic questions about how do we conceptualize mental health and drug safety.
So one more question before we're already cutting pretty deeply into the break, but you will have office hours at 11 o'clock. Right. So for additional questions, you can go to the office hours. So last question from the audience. Do you hold out any hope that statistical incompetence may not always be the norm? You know, I think the question is kind of, can't we do something about this on the human side or the education side as well? Build it more, you know, deeply into curriculum? Do you think that has a chance of solving this problem?
Well, I definitely think that there's an enormous opportunity to improve numeracy at all levels of education, and that we can motivate numeracy by teaching people about empirical inference. And I'm pretty interested in that project. There are people in my department who've tried to teach neuroscientists and doctors various forms of statistics and point out that, you know, the whole math education up through high school prepares people for calculus and linear algebra, but not for probability and statistics. So I mean, at one level, I'm very interested in all of that. And I think, you know, languages and AI systems like BayesDB will help change what you need to teach and what you don't, and that could be powerful because I think our critical faculties may be much better engaged by qualitative thinking than quantitative thinking. Anyway, there's sort of a usual human-machine division there that we could seek differently than currently. That said, I don't think that that will solve the problem. I think we need automation. Secondly, I don't think statistics is enough. I think we need to teach critical thinking and other modes that help people increase their own consciousness of their own psyche. And I don't think anything short of that will really address the root causes. But of course, incremental work towards all these goals is worthwhile.
Yeah, it's a problem to attack on all fronts.
That's
for
right.
sure. Well, how about another round of applause for Vikash Mansinghka? Great talk, great technology.
Thank you.
Thank you very much.
Pleasure.